In this lecture, you will learn about confidence intervals and estimating the mean of a random variable. I'm going to start out with the idea here. We have a random variable x, and we really don't know how it's distributed. I put this graph of a PDF up here just kind of for metaphorical purposes, saying, hey, you don't know how these things are going to be distributed. We do know that it has a mean of mu. We don't know what that is, though. We don't know what the actual number is. And we know it has some standard deviation, but we don't know what the number is. And the idea here is that we want to estimate what the mean of this random variable x is. We want to know what this number mu is. So our first step is to take a sample with size n greater than or equal to 30. Okay. This will change our random variable x. We'll get a new random variable x bar, which is the sample mean for x. And the sample mean is approximately normally distributed with the same mean as the original random variable. And the standard deviation will be the standard error of the mean, sigma divided by the square root of n. Now, we still don't know what these numbers specifically are. We want to estimate them. Here, this graph is drawn with the assumption that mu is equal to 0, and so we will have our values of x bar clustered close about the mean. Okay, now here is the thing we know. We're going to estimate our mu by taking a sample x bar. Okay, take some sample, then take its mean. That mean of the sample will be our estimate, and our estimate will be wrong. That can't be too much. I can't beat it too much into your head. Our estimate will be wrong. There is a probability of 0 that this x bar will be the same as mu. So we have to give ourselves a margin of error that we call E. Okay. And even with that margin of error, there is still a probability that our answer is wrong. So I have it illustrated here in this picture. The idea, say this is our mean here. If we take our x bar can fall anywhere along this axis. But through here, this is where most of the probability is. So this is where our x bar will most likely fall. Now we've set it up so we're giving ourselves a margin of error from here to here, and this over here is beyond the margin of error, and this over here is beyond our margin of error. And so this is, if we get an x bar over here or an x bar over here, we're saying our answer is wrong. So giving ourselves a margin of error is sort of a new definition of what right means. Okay. Now we need to talk about significance and confidence. The significance, which we denote by the Greek letter alpha, is the probability that our estimate is farther wrong than our margin of error. So our alpha is the sum of the probability of the orange and the blue. Okay. The confidence, okay, is another way to talk about the same thing. It's a more positive way to talk about the same thing. 1 minus alpha, it's the complement of the significance. And so whereas our alphas are typically small for what we would consider a good conservative answer, our confidences will be larger for a good and conservative answer. Okay. The margin of error E is the amount of error we allow ourselves so that we can speak about our estimate intelligently. And the formula for the margin of error is given here. E is equal to z sub alpha over 2. And so the alpha over 2 is together. Okay, I'm not dividing z sub alpha by 2. I'm dividing alpha by 2, and the alpha divided by 2 is the subscript of the z. And then sigma over the square root of n, our standard error of the mean. So our margin of error is this z sub alpha over 2, which we'll talk about in a minute, times the standard error of the mean. Okay, so I've drawn this out in a diagram. So we've got our our random variable x bar is its PDF is graphed along this horizontal axis. Okay, we have our it's approximately normally distributed, so we have our mean right here, and I'm saying okay, we want our x bar to be somewhere within that interval. Over here we're wrong. Okay, over here we're wrong. These two on the by symmetry of the graph, they are the same probability, so added together they add up to alpha. Okay, so alpha over 2 over here and alpha over 2 over here. Now, so I can talk about this in kind of a more comfortable way. I take the z-score of it. When I take the z-score of it, I get us, okay, we're still normally distributed, but now our mean is here at 0, and this upper limit of the interval is e divided by our standard error of the mean, and our lower end of the interval is negative e divided by the standard error of the mean. We still have the same probability of alpha over 2 at each end that we had before. So what I'm doing here is saying, okay, say we have one of these normal curves, and I look at one of these tails, okay, the little tail over here. So from this point to this point on out is beta, and so the number where this occurs is z sub beta. Now, in terms of the functions that I'm going to be using to calculate this, I'll need it set up where it's everything up to beta. So I have 1 minus beta is the probability up to here, and so that number will be the percentage point function of 1 minus beta. So ppf of 1 minus beta is the same as z sub beta. Okay, and putting this in terms of our alpha, I'm going to have my ppf of 1/2 plus my confidence divided by 2 is the same as this 1 over beta, this right here. So this right here is the final number that I'm going to be looking for in doing my calculations. So my confidence interval, a p confidence interval for mu, is an interval that we calculate from a sample mu that will be in so that mu will be in that interval a proportion p of the samples. So like for a 98% confidence interval, if we take 100 samples, we more or less expect our mu to be in that confidence interval 98 times. And so this is x bar minus e, x bar plus e is our confidence interval. E is calculated by this formula that I gave you before, and alpha is calculated by 1 minus p, where p is our level of confidence. Okay, So let me give you kind of an example here, the way we would calculate this old school. We'd say, okay, a 95% confidence interval gives me P equals 0.95. And so my alpha is 1 minus P, which will be 0.05. Okay, I'm going to need alpha over 2, so I divide my alpha, my 0.05 by 2 to give me 0.025. And so my z sub 0.025 is equal to 1.960. I do that either by an old school table lookup, okay, or by a PPF calculation that I will show you in the next video lecture. So again, this is stats.norm.ppf.0.975. So what I'm doing, I'm taking 1 minus that 0.025. Okay, and so if my x bar is 1.2 for my sample, and my sample standard deviation is 0.2, and n is equal to 45, I can calculate my E by my formula and get my E equal to 0.06. And so the confidence is 1.2 minus the 0.06 and 1.2 plus the 0.06. And bang, there we have our 95% confidence interval.